as you can see, I've actually marked off everything. I've covered some of 1110 and some of 1111. I'll go back and do some more from here. My lecture will not take the entire time, maybe not even half the time, at which point you can start asking questions in preparation for the test. Okay, so again, first half, I will lecture a while, may not even take the entire first half, and then questions and answers. Now, I'm letting you have Thursday for questions and answers also. So let's quickly review the calendar. We only have 4 days left. Okay, I guess I should mark all these off. But we're here. So exam is Thursday for sure. Okay, so as usual, you submit the homework. So 11.1 to 11.11, 70% rule, as you know. So you must turn in at least 70% of the homework in order for me to count your test. Okay, so normally I would start off with a new section. There is no new section unless you want to start learning some Calc 3, which I don't think you do. So I'll go straight to questions and answers. But again, if you want to get all of your questions out of the way today, then we can hopefully start earlier on Thursday. So I'll start off Thursday by saying, are there any questions? And then we break, quote unquote, which maybe doesn't take that long. Then the rest of the time you can have for the test. Okay, next Tuesday will be sort of like a review for the final. The best way to review is off the old exams. So preferably you would ask questions from previous exams to study for the final exam. Okay, so you say, how do I study for the final exam? Just look at the previous exams. I would draw questions from previous exams for the majority of the final exam. Okay, so our last day, Thursday the 17th, final exam, that's all we're going to do. I won't take any questions on that day. So any questions have to be brought up on the 15th. On the 17th, right at a little bit after 7, I'll send through Canvas announcements the exam, and you get it from there and log on as usual. The only difference, of course, is you don't have to turn in any homework. There's no homework to turn in. And it's the entire time, no change in our timing, so it's still 7:10 to 9:25 for the final exam, 2 hours and 15 minutes. And then that's pretty much about it. Okay, so that's it. So I'll lecture for a while. I'll let you ask questions. When the questions stop, I stop. You can still ask questions on Thursday, but the more we get done today, the less we have to do Thursday. That means the more time you have for the test on Thursday. So Thursday will be the test for sure. I'm moving it up to here. So I'll try to do some more problems from 11:10 and 11:11, but be ready to ask me any questions from anything here. Okay, after I get done with what I'm trying to do. All right, and let's see, somebody put something in the chat, so let me check quickly. Okay, yeah, it's almost too late to tell me, so please send me an email for those of you that just joined. I put away my list, as you know, so I will get started. Okay, oh yeah, the quiz. So quickly on the quiz. So 1 over 1 minus a negative x cubed. This is a, 1 minus r. So the first term is 1. Then you keep multiplying by negative x cubed. 1 minus x cubed plus x to the 6th minus x to the 9th. Integrate. X minus x to the 4th over 4 plus x to the 7th over 7 minus x to the 10th over 10 from 0.5 to 0. 0 gives me 0. 0.5 gives me 0.5 minus 0.5 to the 4th over 4 plus 0.5 to the 7th over 7. Now we are asked to 2 decimal places. And by the way, when it asks to 2 decimal places, you should only give me 2 decimal places. You should not give me 0.48432 or whatever, just 2 decimal places. Okay, I was kind of lenient on the quiz, but I won't be as lenient on exams, perhaps. Okay, the third term is already in the neighborhood of 0.002. That's less than 0.01, which means you should only add the first 2 terms. So 0.5 minus 0.5 to the 4th over 4, rounded to 2 decimal places, 0.48. And there we go. Okay. Now, of course, the nice thing about this, you want greater accuracy, you want 10 digits, just go out farther. Right? This is an infinite series. You can go infinitely far, so you can get accuracy to any desired number of digits you feel like by just going farther and farther out. Okay. So that's that. All right, so getting back to where we were, 11.11. Okay, we're doing Taylor polynomials again. So 11.11, Tn, T stands for Taylor, is an nth degree Taylor polynomial. So before we were doing Taylor series or Maclaurin series. What's a Maclaurin series? It's a Taylor series centered at 0. Okay? It's literally a polynomial at degree n. You just throw out the rest. The rest is called the remainder. Kind of makes sense. R sub n. So f of x is Tn, the nth Taylor polynomial. So you don't write infinitely many terms. You stop. And then you have a remainder, R sub n. Okay. Taylor's inequality says, can I get a handle of how bad my error would be if I stop here? And yes. So absolute value of R sub n is less than or equal to the n plus first derivative, exponent, and factorial. You notice the book says m. It's correct, but I like to do it this way because if I made you memorize this stuff, whoops, if I made you memorize it, it's easy to memorize. Just go to the n plus first, d, e, and f, derivative, exponent, factorial. Maximize this on the closed interval, maximize this on the closed interval. You don't have to say maximize this. This is already fixed, n plus 1 factorial. So we're always on a
closed people are leaving. People are leaving.
Okay. So I'll show you some more of those. Okay. Can somebody mute yourself?
43.
Okay, everybody please mute yourself again. Otherwise, I have to stop. I know it's different now. All right. So I'm going to go back and do a lot of problems from 11.11. And again, these are my problems. They're not necessarily the same as yours, but you're still learning stuff, hopefully. Okay. The beginning problems from 11.11 says find T3, the third Taylor polynomial, which actually means 4 terms. Third degree means there's 4 terms. There's a constant, that's 1 term, and then the x term, and then the x squared, and then x cubed. Okay? And if you stop and think about it, that's exactly what we were doing in 11.10, except in 11.10, we put dot, dot, dot. Now you do the same stuff, put 4 terms, you don't put the dot, dot, dot. We're actually coming up with a third degree polynomial. Okay, so that's all. So f of x is 1 over x at a equals 2. I don't know if this is the same as yours or not, but maybe, maybe not. Okay, once it says centered at a equals 2, and by the way, you might say, why don't we just always center at a equals 0? You're not allowed to have 0 here, as you can see, right? So centered at a equals 2. So right away, I know it's x minus 2 to the 0 over 0 factorial. Yes, that's 1. Yes, that's 1. But once I write this, I know how to write all the rest of the stuff. X minus 2 to the 1 over 1 factorial. X minus 2 squared over 2 factorial. X minus 2 cubed over 3 factorial. If you had to go to the 100th exponent, it'd be x minus 2 to the 100th over 100 factorial. Right? It always matches. So the e exponent and the f factorial are already determined. Okay, what's going to change from problem to problem are the d's, the derivatives. So I take my derivatives. So f of x is 1 over x. Change it to x at a negative 1. You don't want to do the quotient rule unnecessarily. Okay, so the first derivative is negative x at a negative 2. Second derivative is 2x at a negative 3. Third derivative is negative 6x at a negative 4. This is better for calculus, but this is better for algebra, right? Negative 1 over x squared, 2 over x cubed, negative 6 over x to the 4th. Now I plug in 2 everywhere. Wherever you're centered, that's what you plug in. So f of 2 is 1/2. F prime of 2, put a 2 here, negative 1/4. F double prime of 2, put a 2 here, 2 over 8, 1/4. Triple prime, put a 2 here, negative 6 over 16, negative 3/8. So the numbers I put in front, the d's, are 1/2, negative 1/4, positive 1/4, negative 3/8. And clean it up. This is always going to be 1, so 1/2. Negative 1/4 divided by 1 is negative 1/4, so minus 1/4, x minus 2. 1 over 4 times 2, remember that 4 can just sneak down and join the 2. So 1/8, x minus 2 squared. 8 comes down, 3 factorial 6. 6 will cancel the 3, leaving with 2 in the bottom. 2 times 8 is 16. So minus 1/16, x minus 2 cubed. So if you ask for the best cubic, third degree polynomial approximation to 1 over x, this would be it, near x equals 2. We're just not putting dot, dot, dot. We're not just going infinitely far. We're just stopping here. So T3 is the best cubic approximation. T2 is the best quadratic approximation, parabola. What did you do in a lot of Calc 1? A lot of Calc 1, you did T1, the best linear approximation, right? The tangent to the curve you did in Calc 1, right? Okay, and then my number 5. Okay. So my number 5, cosine x, a equals pi over 2. And again, the directions say find T3. I'm just curious if it actually says that here. It's not the very same question. Yeah, it does say find T3 in directions. Find the polynomial T3 of x, which means you need 4 terms. Constant term, x squared, x cubed. Exactly like all the previous ones where I gave the Melvin-Harm rule of putting down at least 4 terms. And then before we put dot, 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 now we don't put dot, dot, dot. Okay, so cosine x. First derivative, negative sine. Second derivative, negative cosine. Third derivative, sine. We're centered at pi over 2. That means you keep plugging in pi over 2, and it's going to be x minus pi over 2 to the 0 over 0 factorial. X minus pi over 2 to the 1 over 1 factorial. X minus pi over 2 squared over 2 factorial. X minus pi over 2 cubed over 3 factorial. That's exactly what I would have written before, except don't put the dot, dot, dot. We stop, so just don't put the dot, dot, dot. Okay, now I plug in pi over 2. Pi over 2 is 90 degrees. Cosine of 90 degrees is 0. Sine of 90 degrees is 1, but the negative means it's negative 1. Negative cosine of pi over 2 is negative 0, which is 0. Sine of pi over 2, 1. So 0, negative 1, 0, 1. Gone, gone. Now, the problem asks for a third degree polynomial. So there's only going to be 2 terms. That's okay. You don't have to keep going to 4 terms. In fact, you should not here if it just says third degree. So I only have that and that, which I'm rewriting as negative 1, which is negative x minus pi over 2, plus 1/6 x minus pi over 2 cubed. Final answer. Okay. Okay. Line number 7, ln x, it does match this time at least. ln x centered at a equals 1. You cannot center at a equals 0 because we can't take ln of 0. They ask for T3, so I want 4 terms. Okay, so f of x is ln x, f prime is 1 over x, which is x at negative 1. Second derivative is negative x to the negative 2, which is that. Third derivative is 2x to the negative 3, which is that. Centered at 1, plug in 1, plug in 1, plug in 1, plug in 1. Okay. X minus 1 to the 0 over 0 factorial. Yes, that's 1. Yes, that's 1. But once I have that pattern, I got all the rest. X minus 1 to the 1 over 1 factorial. X minus 1 squared over 2 factorial. X minus 1 cubed over 3 factorial. Okay, that's 1, that's 1, that's 2, that's 6. Okay, plug in 1, natural log of 1 is 0. Plug in 1, 1 over 1 is 1. Plug in 1, negative 1 over 1 is negative 1. And 2 over 1 is 2. So 0, 1, negative 1, 2. 0, 1, negative 1, 2. So that's gone. This turns into x minus 1 over 1, or just x minus 1. This is negative a half x minus 1 squared. 2 over 6, 1/3 x minus 1 cubed. This is the best cubic, third degree approximation to the natural log function near a equals 1. Okay. Calc 1, it was always just linear, right? Give the straight line approximation. This is the best cubic. So you say, give me a cubic function which looks most like the natural log function. Here it is. This is a polynomial. We like this way better than ln. ln is still a mystery to a lot of us, but this is not as mysterious. Okay, 9, I do not use the same technique. because I don't like taking all the derivatives of this. I just derive from the formula for e to the x and go from there. Okay, and it's a Maclaurin series centered at a equals 0. Okay, now I could do the same trick as here and here. That means I need to take 3 derivatives of this. I don't want to take 3 derivatives of this. You probably don't want to take 3 derivatives of this either. It's a product root and chain root, right? First times derivative of the second plus second times derivative of the first, and then times -2. And then the second derivative, you got to do something that's probably more complicated. And the third derivative, you probably have something more complicated than that. Instead, start off with the expansion for e to the x and build from there. From here, treat as a function, plug in -2x, and then multiply by x. Okay, so here's how it works. So here's the expansion for e to the x. Again, you can just get that right off that page I gave you guys, right? Let me see if I can. So if you haven't already done so, put this on your formula sheet, page 768, right? Formula from 1 over 1 minus x, e to the x, sine x, cosine x, inverse tangent x, ln 1 plus x. And don't worry about that last one. Right? Okay, so e to the x to the 0 over 0 factorial, x to the 1 over 1 factorial, x squared over 2 factorial, x cubed over 3 factorial. 4 terms. Now, e to the -2x, just like any other function, replace this and this and this and this with parentheses -2x. So -2x to the 0, -2x to the 1, -2x squared, -2x cubed. Okay, I cleaned that up. This is 1. If you can't read that, that's a 0 there. Anything to 0 is 0, 0 factorial. I'm sorry, anything to 0 is 1. 0 factorial is 1. 1 divided by 1 is 1. That's -2x. -2x squared is 4x squared divided by 2 plus 2x squared. This is -8x cubed over 6. -8 over 6, -4/3 x cubed. Now you simply multiply by x. So that becomes x minus 2x squared plus 2x cubed minus 4/3 x to the 4th plus ... Okay. But they asked for T3, which means it has to be a cubic. So I throw out everything here and on, and I just put x minus 2x squared plus 2x cubed. And there we go. Okay. Okay, and now for some more problems involving Taylor's inequality that I showed you, right? Which means use this stuff. Remainder theorem. Taylor's inequality, page 762. So absolute value of r sub n of x less than or equal to. They put m. It's easy to memorize. I know you're not memorizing, but just to be consistent, if you put that there, it's basically the n plus first derivative, exponent, factorial, in absolute value. So absolute value here, here. You don't have to say absolute value here. This is already positive. And that's an estimate for the remainder. Okay, so that's problem, let's see, 13 through 21, of which I showed you a couple last time. And I'll try to do more now. Okay, let me see. Okay, so my problem 15, x to the 2/3. And does that match? It does match, I think. Yeah. Set it at a equals 1, n equals 3, from 0.8 to 1.2. So first come up with the third degree Taylor polynomial, and then what's my error, the maximum error possible. So I need T3, but I actually have to go to the fourth derivative by the theorem, we said, right? The remainder is based on the n plus first derivative, exponent, and factorial. All right, x to the 2/3. First derivative is 2/3 x to the -1/3. Second derivative is -2/9 x to the -4/3. third derivative is positive 8 over 27, that times that, right? X to the negative 7/3. Okay, so I can stop right here if I just want T3, the third Taylor polynomial, but I have to go to the fourth derivative in order to get an estimate for the error, we said, right? By Taylor's inequality. So I need the fourth derivative, so it gets kind of clumsy, but that times that is negative 56 over 81, x to the negative 10/3, which I'm going to write like this, negative 56 over 81, x to the 10/3. All right, we're centered at 1. I keep plugging in 1. Very conveniently, 1 raised to anything is 1. So if you put a 1 here, and a 1 here, and a 1 here, and a 1 here, that's just 1. So the function value is just going to be the coefficients. So f of 1 is 1, f prime of 1 is 2/3, f double prime of 1 is negative 2/9, f triple prime is 8 over 27. All right, so they want a third degree polynomial. So here we go. Centered at 1, x minus 1 to the 0 over 0 factorial, x minus 1 to the 1 over 1 factorial, x minus 1 squared over 2 factorial, x minus cubed over 3 factorial. Yes, that's 1. That's 1. Okay, and what do I put in? 1, 2/3, negative 2/9, 8 over 27. 1, 2/3, negative 2/9, 8 over 27. And then I clean it up. Yes, that's 1. 2/3 divided by 1 is 2/3. X minus 1 to the 1. I know it's 1. Okay, let's see. This is negative 2/9. So the 9 joins the 2. The 2's cancel out. So negative 1/9, x minus 1 squared. Okay, 8 over 27 joins the 6. 3 factorial 6. 8 divided by 6 is 4/3. So it's 4 over 27 times 3, 81. Okay, so instead of using this weird function, x to the 2/3, I can replace it with a third degree polynomial. This is a third degree polynomial approximation of the function. You say, well, that's not fair. They're not the same function. Yes, but we are going to come up with an estimate of the error if we're plugging in stuff between 0.8 and 1.2. Okay, so here's what we do. So I use the formula. Absolute value of r sub n of x. I go to the n plus first derivative, exponent, and factorial. So the fourth derivative in absolute value, fourth exponent, and 4 factorial. Okay. And if I have absolute value, you know you can drop the minus sign, right? Okay, we've seen this before. If x is in the bottom, I can make this expression the biggest if I pick the smallest number. Is that right? By the reciprocal rule? If x is in the bottom, I would make it biggest by plugging the smallest, which is 0.8. So 56 over 81, 0.8 to the 10/3. What number in this interval would maximize this quantity? Either 0.8 or 1.2. If I plug in 0.8, that would be a negative 0.2. If I plug in 1.2, it would be positive 0.2. It doesn't matter. It's the same thing raised to the fourth power. So 0.2 to the fourth over 4 factorial. So there it is. Notice it's a different game. You work out this game separately than this. You don't have to pick the same x value for this as this. It's almost have to say, work on this, just what number between 0.8 and 1.2 inclusive would maximize this. And then new question, what number between 0.8 and 1.2 maximizes this? Okay, you punch it in a calculator. 56 over 81 times 0.8 to the 10/3 times 0.2 to the fourth over 4 factorial, which is 24, comes out to be about 0.0001. Okay, what does this mean? If I cheat, and instead of using the actual function, I used a cubic polynomial, you say, well, they're not going to be the same. You're right, but the error is no more than 0.0001, which is not too bad, if that's good enough for you, so to speak. So I'll be no more than this off, as long as I pick stuff between 0.8 and 1.2. Okay, so that's the way the theorem works. Okay, then 17 was next, and let me see if it matches. 17 secant of x? Yes, exactly the same. So secant of x, centered at 0, I like that. chlorine series, n equals 2 between negative 0.2 and 0.2. Okay, side note, I'm going to need these. The secant of 0 is 1. Secant is the reciprocal of the cosine. Cosine of 0 is 1. Flip it, it's 1. Tangent of 0 is 0. Okay, I'll need that. Okay, so function is secant of x. N equals 2 means I'm replacing the secant with a quadratic, a parabola. Instead of using a secant of x, I'm getting the best parabolic approximation. Okay, f prime is secant x tangent x. F double prime, unfortunately I have to do the product rule. So first times derivative of the second, secant times secant squared x, plus second function, tangent x, times derivative of the first, secant x tangent x. So this cleans up to be secant cubed x plus secant x tangent squared x. That's all I need if I just want T2. But if I want an approximation for the air, I do have to go to T3, the third derivative, unfortunately. So I have to differentiate this mess. So here we go. Derivative of this, 3 secant squared x times the derivative of secant x by the chain rule, secant x tangent x. Plus, what's the derivative of this? Product root. First, secant x times the derivative of the second, derivative of tangent squared is 2 tangent x times derivative of tan x, which is secant squared x, plus second function, tangent squared x, times the derivative of the first, derivative of secant x is secant x tangent x. Okay, now, let's see what I can do with this. I have 5 secant cubed x tangent x. There's 3 right here, and there's 2 right here. That's 5 secant cubed x tangent x. And then I have an extra secant x tangent cubed x. Okay, that's the third derivative. Okay, now I plug in 0. Secant of 0 is 1. F prime of 0, I got a tangent of 0, so that's 0. F double prime of 0. 0 here makes this 0. 0 here makes it a 1. So I have 1, 0, and 1. I'm centered at 0. I only want T2, which means a second degree polynomial. It's a parabola. So x to the 0 over 0 factorial, x to the 1 over 1 factorial, x squared over 2 factorial, 1, 0, 1, 1, 0, 1, 0 makes that gone. So 1 plus 1/2 x squared. So this is the best parabolic approximation to the secant function near the point 0, 1. And if you stop and think about it, okay, if you might recall the secant function, it is kind of U-shaped at 0, 1. And so the best parabola approximation is 1 plus 1/2 x squared. They're not the same. So we're going to have some kind of error. Yes, but we can get an approximation for the error between negative 0.2 and 0.2. Okay, so our estimate for the error, R2 of x. So notice the notation. It's the remainder if I have the second degree polynomial. We write absolute value of R2 of x, but you have to go to the third derivative exponent factorial. So here was my third derivative. Where'd it go? All of that. So notation is R2 of x, but third derivative exponent factorial. Okay, if it's R4, fourth degree polynomial, it's the fifth derivative exponent factorial by rule. Okay, so we're plugging in stuff between negative 0.2 and 0.2. Okay, so what maximizes this? Either 0.2 or negative 0.2. So that's that. Okay, this might be kind of hard to convince you of this, but 0.2 does maximize this and this. If you think of the way the tangent function, tangent goes up near the origin, and so does the secant. So 0.2 would maximize that, and that, and that, and that. So I plug in 0.2 here, and here, and here, and here. Okay, you can punch that in your calculator. This is a little bit clumsy, because you don't have a button that does secant, but we know secant is a reciprocal of the cosine. You do have a tangent button, so you can punch that directly in radians. It's got to be in radians. This, you'd have to put it in a denominator as 1 over cosine cubed. Anyway, I already did it before, so save you some time. 0.002. Okay, so what does that mean? Instead of using a secant function, oh, very inconvenient, I use a parabola. I like that better. There's going to be an error. The error is no more than 0.002. 2 parts in 1,000, 1 in 500, as long as I pick something between negative 0.2 and 0.2. Okay. Okay, then 19, e to the x squared, 0, 3. This one is the same also. That's nice. So that's that. Unfortunately, this one I can't just use a shortcut for e to the x. I do need the fourth derivative. So I do a whole bunch of derivatives for this, unfortunately, but be that as it may. But at least it's a Maclaurin series. I'm centered at 0. So n equals 3, automatically, even before I start, x to the 0 over 0 factorial, x to the 1 over 1 factorial, x squared over 2 factorial, x cubed over 3 factorial. Okay. All right, e to the x squared. First derivative is e to the x squared times 2x. Second derivative, well, product rule. 2x times the derivative of e to the x squared, we just did that, 2x e to the x squared, plus the second function, e to the x squared, times the derivative of the first. Derivative of 2x is 2. Clean this up a little, that's 4x squared plus 2, right? So 4x squared plus 2, e to the x squared. 2 more derivatives. Triple prime. So product rule again. First times the derivative of the second. What's the derivative of e to the x squared? We just did that. 2x e to the x squared. Plus the second function, e to the x squared, times the derivative of the first. Derivative of that is 8x. Okay, and now if you clean this up, let's see, you get 8x cubed plus 12x e to the x squared. Okay, so that's going to be 8x cubed. This is 4x plus 8x, so 12x. So if I only wanted T3, I would stop there. But since they want an estimate for the air, you actually need one more derivative, unfortunately. So I have to take the derivative of this. Very clumsy. So here's the fourth derivative, F4. You'll notice the notation, F prime, double prime, triple prime. Once you go to the fourth derivative, just write the number. Don't put 4 apostrophes, that's too much. All right, so one more product rule. First, times the derivative of the second, the derivative of e to the x squared, we already did that, 2x e to the x squared. Plus second function, e to the x squared, times the derivative of the first. Derivative of this is 24x squared plus 12. So clean it up. That times that is 16x to the fourth. Okay, plus 24x squared plus another 24x squared, that's 48x squared, plus 12 e to the x squared. So we finally have it. Okay, we're between 0 and 0.1. Now I keep plugging in 0. So even though these are messy, it's nice to plug in 0. E to the 0, 1. 0 here makes the whole thing 0. 0 here, let's see. E to the 0 is 1. 0 here, that gives me 2. Plug in 0 here and here, that makes the whole thing 0. So 1, 0, 2, 0. 1, 0, 2, 0. That's gone. That's gone. So T3 is 1 plus x squared. So what does that mean? The best approximation for the function e to the x squared near the origin is 1 plus x squared. That's not fair. There's going to be some error. That's right. But we can find a maximum error. In this case, it's pretty small. So as long as I pick a number between 0 and 0.1. So notice the notation. absolute value of R3 of x, the error upon using T3. What are we supposed to use? We're supposed to use infinitely many terms. So instead of infinitely many terms, I stop at the fourth term, which is T3. Okay. My error is no more than the fourth derivative exponent factorial. Okay, so here's the fourth derivative, fourth exponent. I'm centered at 0, so just x to the fourth over 4 factorial. Okay, how do I maximize x to the fourth between 0 and 0.1? I just pick the biggest number, right? It's not going to be 0. 0 gives me 0. How do I make x to the fourth biggest? Plug in 0.1, the biggest number. How do I make this expression the biggest between 0 and 0.1? Again, plug in the biggest number. 0.1 here, 0.1 here, and 0.1 here. So 16 times 0.1 to the fourth plus 48, 0.1 squared plus 12 times e to the 0.1 squared. That would maximize this quantity. Times 0.1 to the fourth over 4 factorial, which is 24. Okay, punch this all in the calculator, 0.00006. All right, so what does it mean? Instead of using this weird function e to the x squared, I replace it with a much nicer function, 1 plus x squared. Well, that's not fair. It's a different function. But the error is no more than 0.00006, which is pretty good. That's as long as you plug in a number between 0 and 0.1. That's what we're saying there. Okay. All right, then problem 21, and then I'm done. Let's see, x sine x, a equals 0, n equals 4, from -1 to 1. Yes, it matches. Okay, so after I do 21, I'm finished, folks. And it's getting almost to be break time, but that's sort of up to you. Okay, so 21's it. So if you want to start asking questions, you may, or if you want to start putting in the chat, I suppose you can. Because otherwise, I'm marking this off. I'm finished. Okay, so if you want to start asking me stuff anywhere here, it's fine, because otherwise I'm finished. Okay, so think about what you want to do. I'll be finished with my last question, 21, in a couple of minutes. Okay. Okay, x sine x, a equals 0, n equals 4, from -1 to 1. So instead of using x sine x, I'm replacing it with a fourth degree polynomial, degree 4. But to find the error, I have to go to the fifth derivative and exponent and factorial. Okay, unfortunately, there's a product group. I have to do it 5 times. But fortunately, this is the last problem that we're doing, okay? All right, x sine x. And another nice thing is we're centered at 0. It's a Maclaurin series. And we're estimating between -1 and 1. Okay, so first derivative, product group, first times derivative of the second, x times cosine x, plus second function, sine x times the derivative of the first, which is 1. Okay, second derivative, product group, first times derivative of the second, x times negative sine x, plus second function, cosine x times the derivative of the first, which is 1, plus derivative of sine x, which is cosine x, cos x, 2 cosine x. So negative x sine x plus 2 cosine x. Triple prime, product group. First times derivative of the second, negative x times cosine x, plus sine x times the derivative of the first, which is -1. Then the derivative of 2 cosine x is -2 sine x. Negative x cosine x minus 3 sine x. There actually is a nice pattern. You might notice it's 1, 2, -3, -4, 5, and so on. Anyway, you don't need to know that. Fourth derivative, notice the notation. We don't write prime, 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 prime. We just write the number 4. Okay, product group. First times derivative of the second, negative x times negative sine x, plus second function, cosine x, times the derivative of the first. Derivative of negative x is -1. Derivative of -3 sine x is -3 cos x. So it's -3 cos x minus cos x minus 4 cosine x. So here's my fourth derivative. So that's all I would need if all I needed was T4. but I need the fifth derivative exponent factorial to find the error. Remember what's happening before we did the alternating series estimation theorem, but we can use Taylor's inequality even if it's not alternating, like e to the x. Okay, so how do you find an error if you don't have an alternating series? Then you use this Taylor's inequality. All right, fifth derivative. What's the derivative of x sine x? X cosine x plus sine x times the root of the first, which is 1. Derivative of -4 cosine x is positive 4 sine x. That plus that, so x cosine x plus 5 sine x. So there we go. All right, so we've never done so many derivatives in our lives yet, right? Okay, so function, first derivative, second derivative, notice there's a 2. Third derivative, notice there's a 3. Fourth derivative has a 4, actually negative. Fifth derivative has a 5, but anyway, be that as it may. Okay, now I plug in 0. Sine of 0 is 0, cosine of 0 is 1. So 0, that's gone. 0 here, that's gone, and that's gone. So that's also 0. Plug in 0 here, that's gone. Cosine of 0 is 1, so that gives me a 2. Triple prime. 0 here gives me 0. Sine of 0 is 0. A lot of zeros, very nice. Fourth derivative, plug in 0, that's gone. Cosine of 0 is 1, so -4. So here's T4. X to the 0 over 0 factorial, x to the 1 over 1 factorial, x squared over 2 factorial, x cubed over 3 factorial, x to the 4th over 4 factorial. I don't need the dot, dot, dot. I'm stopping. 0, 0, 2, 0, -4. 0, 0, 2, 0, -4. Gone, gone, gone. 2 divided by 2 is 1, so x squared. -4 over 4 factorial is 24. -1/6 x to the 4th. Okay, so instead of using this messy function, I replace it with this. Much nicer. That's not fair, you're right. But I can get an estimate of the error if I have something between -1 and 1. So here we go. Absolute value of R4, what's the error? It's no more than the fifth derivative exponent factorial. Okay. Between -1 and 1, what maximizes absolute value of x to the fifth? Well, if I plug in either 1 or -1, it'd be 1. Right? If I plug in 0.9, it'd be less than 1, and so on. So 1 maximizes that. How do I do this stuff? Okay. Cosine x and sine x have a maximum value of 1. We already know that. So I'll just call that 1. I'll call that 1. How do I maximize x between -1 and 1? With a 1. So 1 times 1 plus 5 times 1 is 6. Times 1 to the 5th over 5 factorial, which is 120. So that's 1 over 20, or 0.05. Okay, so my error is no more than 0.05, and that pretty much is it. Okay. And I'm done, folks. Okay, so now I can go to review questions. Okay, so let me check the chat and start writing some of this stuff down. Okay, let's see. Go back up. Write some of these down. Okay, question 19, question 9. Okay, 11.931, 11.172, 11.245, 11.931. Why couldn't we do question 19 like question 9? I'm assuming you mean from the last section. 19 like 9, yes. Okay. For question 19, unfortunately, we have to go to the fourth derivative in order to use this formula. Okay. Now, if it didn't ask for this, I would do 19 like problem 9. But unfortunately, I have to get the fourth derivative. There's no way around it. So that's why I had to actually do the fourth derivative. If it only asked for the third Taylor polynomial, yes, I would have done that problem 19 the exact same way, as it turns out. Okay. All right. Let me see. What time is it? 8 o'clock. Might want to break at some time also. Okay. 931. Okay, 11.1, 72, 45, 11.4, 27, and 9. Okay, 11.3, 23, 25, 11.6, 17, 21, 31, 11.4, 25, 11.6, 21, 23, 7.9, 11. I'll go back up like that. Okay, let's see, what time is it? 8 o'clock? Okay, maybe I'll get started with some of these, and then maybe we'll break and then keep going after that. So let's see how far we get, okay? All right, so I'm going to put away the chat. So you can keep putting stuff in the chat if you wish, but I won't be able to see it right now. Okay, 11.9. $31. 1.931. Integral from 0 to 0.2. X ln 1 plus x squared dx. Nope, I got that backwards. X squared ln 1 plus x. Sorry. Okay, so use the formula for ln 1 plus x. This thing. Okay, so I'll go x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. Okay. X cubed over 3 minus x to the 4th over 4 dx. And then I distribute x cubed minus 1/2 x to the 4th plus 1/3 x to the 5th minus 1/4 x to the 6th plus dot 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 dx. So that's x to the 4th over 4 minus 1/2 x to the 5th over 5 plus 1/3 x to the 6th over 6 minus 1/4 x to the 7th over 7 plus dot 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 from 0 to 0.2. I forgot to write down how many decimal places do they want for this. Six decimal places, which means 10 to the minus 6 accuracy. Okay, plug in 0, you get 0. So just plug in 0.2. 0.2 to the 4th over 4 minus 0.2 to the 5th over 10 plus 0.2 to the 6th over 18 minus 0.2 to the 7th over 28. That's dot, dot, dot. That converges by the alternating series test. So let's try to find something that's less than 10 to the minus 6. I wonder if that one is the third one. Don't know until you try it. 0.2 to the 6th divided by 18. 3.5 times 10 to the negative 6, not quite. I hope it's the next one. 0.2 to the 7th divided by 28. Yes, 5 times 10 to the negative 7. So I just add up these terms. Okay, I do that quickly. 0.2 to the 4th divided by 4 plus 0.2 to the 5th divided by 10 plus 0.2 to the 6th divided by 18. Point 0.00436 to 4 decimal places. Yeah. Okay. Well, let's see. It's almost 8:05, so we'll go ahead and break. So we'll break and start up again about what? 8:15, 8:15, 8:16, something like that. Okay. Okay, folks, let's continue on. Check something. Okay, so the one I just did actually wasn't it. My I went from 31 up to 27. So I got the limits from 0 to 0.2. And then my I went over to did 27. So that problem doesn't exist, unfortunately. So I have to start over again, I guess. So here we go. All right, so I start with ln x. So ln x is, this was it. X minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, dot, dot, dot. Okay, let's see. ln 1 plus x squared. 1 plus x squared minus 1 plus x squared over 2 squared over 2 plus 1 plus x squared cubed over 3 minus 1 plus x squared to the 4th over 4. Okay, that's going to be much too much work to work out. So let me think if there's a better way to do that. Better way to do that is with a substitution, or this is going to take so long. I think I might just have to throw that one out. Okay, I'm throwing out 11.931, sorry. If I complete that, it's going to take me so much time. I'd end up being half an hour, and I don't think it's worth the extra time to do that to work this out. Unless there's something nice I don't see right now. A nice thing you could do is to do a U substitution, but that wasn't the idea behind the problem. Okay, so we're going to skip that one. So I'm throwing it out. Okay, 11.927. Well, I sort of did that over here. So 11.927, just don't plug in stuff here. So 11.927, throw that out, put C in front, and that's it. Okay, so 1/4 minus 1/10 plus 1/18 minus 1/28, and that's it. So that's 27. Okay, so that's kind of a cheap way for me to do that, but be that as it may. Okay, 11.172. 11.172, a sub n is cosine n. Okay, so it bounces between -1 and 1. So it's definitely bounded between -1 and 1. It's not monotonic because it just keeps going up and down, right? So we know it keeps going up and down, so not monotonic. Okay, so that's that. 11.245. Three over n times n plus 3 as a telescoping series. Okay, so I have to use partial fractions for this. So 3 over n times n plus 3 equals a over n plus b over n plus 3, n plus 3, n plus 3, and n. So an plus 3a plus bn over n times n plus 3, which is a plus b times n plus 3a over n times n plus 3. And that's supposed to be equal to 3. So this coefficient is 0. This coefficient is 3. So a plus b equals 0. 3a equals 3. So that means a equals 1, b equals -1. Okay, so S is summation n equals 1 to infinity. This is now 1 over n minus 1 over n plus 3. Okay, so to come up with a formula, let me just actually do, let's say, the first, how many terms do I want? 6 terms, might be enough. S6. So plug in 1, 1 minus 1/4. Plug in 2, 1/2 minus 1/5. Plug in 3, 1/3 minus 1/6. Plug in 4, 1/4 minus 1/7. Plug in 5, 1/5 minus 1/8. Plug in 6, 1/6 minus 1/9. Okay, now let's see what cancels out. 1/6 cancels out. 1/5 cancels out. 1/4 cancels out. 1, 1/2, and 1/3 do not cancel out. Neither do the -1/7, -1/8, or -1/9. Okay, so it's 1 plus 1/2 plus 1/3 minus 1/7 minus 1/8 minus 1/9. That's S6. That same pattern is going to hold all the way through. So now I can say Sn. So it looks like we don't cross off the last 3 negatives. So you have 1 plus 1/2 plus 1/3 minus 1 over 7 is n plus 1 minus 1 over n plus 2 minus 1 over n plus 3. All right, and then the limit as n approaches infinity of Sn. When n gets big, that's 0, that's 0, that's 0. So you just have the first 3 terms, 1 plus 1/2 plus 1/3, which comes out to be 11/6. Okay, so that's how that one works. Okay, 11.3, 23 and 25. Okay, for 11.3, I'm probably going to declare, now that we know other tricks, just use other tricks. So 11.323, okay, you can integrate that by parts, but now that you know other rules, 23, I would say use the ratio test. 25, use limit comparison test to 1 over n cubed. You know that for super big n, the n squared drops out. Okay, so for 23, I would use the ratio test. Pretend it's k over e to the k. 25, do a limit comparison test to summation 1 over n cubed. Okay, so maybe I'll show you 25 in that fashion. So what am I doing? 11.325, summation 1 over n squared plus n cubed. So compare to summation 1 over n cubed. Limit n approach infinity, 1 over n squared plus n cubed over 1 over n cubed. Multiply top and bottom by n cubed. N cubed, so that cancels out. N cubed over n squared plus n cubed. Okay, that's going to be 1. Okay, you can divide top and bottom by n cubed to do that, or you can do L'Hopital's rule. It's basically 1. Okay, which means whatever happens to this one happens to this one. Summation 1 over n cubed converges because it's a p series, where p is equal to 3, which is greater than 1. Therefore, the original series also converges by limit comparison test. Okay. That's what I want to do for that one. 11.4, 27, 9, and 25. A little bit out of order there. 11.4, number 9. Okay, I think we did that one. Summation ln k over k. You could actually do the integral test, but I would compare to summation 1 over k, where ln k is greater than 1 for k greater than 3. We saw that. And then if I divide both sides by k, I have this. And summation 1 over k diverges because it's the harmonic series. Harmonic series. Therefore, the original series also diverges. The smaller series diverges, so the bigger one also diverges by comparison test. Okay, and 27 was asked for. It's hard for me to keep track of what I got here. 9, 11.427, I think it is. One plus 1 over n squared e to the negative n. I think it was 1 to infinity. 1 plus 1 over n squared over e to the n. Okay. If I plug in 1, I get 4. If I plug in anything else, it's less than 4. So I would do a comparison test with 4 over e to the n. So compare to summation 4 over e to the n. Okay. 1 plus 1 over n squared is less than or equal to 4. If you plug in 1, you get exactly 4, right? 1 plus 1 is 2. If you plug in 2, it's 3 over 2 squared, which is less than 4. If you plug in super big numbers, if you plug in 1,000,000, it's practically 1 squared. Okay, so I have this, and then I divide both sides by e to the n. Okay, and summation 4 over e to the n converges because it's a geometric series. Common ratio is 1 over e, and 1 over e in absolute value is less than 1. This series is 4 over e squared, 4 over e cubed. You keep multiplying by 1 over e. 1 over 2.7, that's less than 1. Okay, so therefore, the original series also converges by the comparison test. Okay. The bigger series converges, so the smaller series converges, and you have only positive terms here. Okay. All right, 11.425. We keep track here. e to the n plus 1 and e to the n plus 1. Okay, well, for super big N, forget about the plus 1s, right? E to the n divided by n e to the n, 1 over n, right? So compare to summation 1 over n, right? When n is super big, forget the 1s. E to the n's drop out, it's 1 over n. Now prove it. E to the n plus 1 over n e to the n plus 1 divided by 1 over n. Multiply top and bottom by n. So limit n approach infinity. N e to the n plus n over n e to the n plus 1. You can do L'Hopital's rule or divide top and bottom by n e to the n. Let's do that. Divide by n e to the n, divide by n e to the n. Limit n approach infinity. 1 plus 1 over e to the n. 1 plus 1 over n e to the n. And now when n gets big, that's 0, that's 0. So 1 plus 0 over 1 plus 0 equals 1. Which means whatever happens to this happens to this. What happens to this? It diverges because it's a harmonic series. Okay, so going up top now, got to finish on top. Yes, I know I'm going fast, but I want to get as many questions as possible. So I'm aiming for quantity more than quality. You can always play back the video. Okay, so summation 1 over n diverges. Reason, it's the harmonic series. Therefore, the original series also diverges by limit comparison test. Okay, let's see, 11.6, 17, 21, 23, and so on. Let's take a look. 11.6, 21. 11.6, 21. Now, I almost don't even want to write it, but let me just, excuse me, let me just write the general term. Negative 1 to the n minus 1, n factorial over 1 times 3 times 5. It's the odd factorials. Okay, so they have all this other stuff. I'm cheating a little bit. I'm just not putting the front stuff because it takes too long to write. The main thing is that this is the nth term right here. So it's the factorials over the odd factorials, so to speak. Absolute value of a sub n plus 1 over a sub n. N plus 1 factorial, 1 times 3 times 5, 2n plus 1 minus 1 factorial. This is equal to 2n plus 1. So the term just before that is 2n minus 1. They're 2 apart. Flip this, 1, 3, 5, 2n minus 1. Whoops. Sorry, there's no factorial here, just 2n plus 1. Sorry, there's no factorial there. And this is just n factorial, right? Okay, n plus 1 factorial divided by n factorial is n plus 1 on top. All of these cancel all of these, and you have a 2n plus 1 left over on the bottom. And that approaches 1/2. as n approaches infinity. So therefore, the series is absolutely convergent by the ratio test. Okay. So what was that one? 21? I didn't even write it down. Oh, I wrote it down here. It's 21. 17. Cosine n pi over 3 over n factorial. I'll aim for absolute convergence. Absolute value of cosine n pi over 3 is positive. It's definitely less than or equal to 1. And then divide both sides by n factorial. Okay. Summation 1 over n factorial converges absolutely by the ratio test. And we've already seen that a couple places. Problem 11 does that, but I'm pretty sure we did it a couple places. Well, let me just state that. I'm sure I did it at least twice, so you can find that back. I can't find it right now with so many things going on. But anyway, therefore, the series is absolutely convergent by the comparison test. Okay, so the bigger series converges. So this thing smaller also has to converge absolutely by the comparison test. Okay, so that's 17.
My thing on that one was that you can do absolute convergence by the comparison test.
Absolute convergence, right. So I aim for absolute convergence, and that automatically means convergence too.
So you don't necessarily have to use the ratio or the root test.
You don't necessarily have to, but this one you have to do the comparison test. And yeah, you would prove this by the ratio test for sure. You're going to end up with a n plus 1 factorial on the bottom and an n factorial on top, I believe it was.
Okay, cool. Thank you.
Yeah, all right, you're welcome. And let's see, where was I? I lost my place, which is easy to do when I'm in this situation. So if I missed your question, just go ahead and ask it again, or you can ask it again on Thursday. 11.6 is where I'm at. I think I was about to cross it off, but I missed it. 31. Okay, finish with that paper. Summation -1 to the n over ln n 2 to infinity. What's wrong with 1? Can't take ln 1. All right, it's alternating, terms decrease in absolute value and approach 0. All right, alternating absolute value is decreasing, a sub n approaches 0. Therefore, the series converges by the alternating series test. Is it absolutely convergent? The answer is no. So I take the series of the absolute values, which basically means drop the -1 stuff. We've seen before that this actually diverges because n is greater than ln n. We've seen this before. If you think of the graph, here's y equals x, here's ln x. So x is greater than ln x, which means n is greater than ln n. The reciprocal root says 1 over n is less than 1 over ln n. And summation of 1 over n diverges because it's the harmonic series. Harmonic series. So the smaller series diverges to infinity. Therefore, this one also diverges. So therefore, summation 1 over ln n also diverges by comparison test. So by definition, therefore, the original series is conditionally convergent, which means the series converges, but if I take the absolute value of all the terms, it diverges. So by definition, that's called conditionally convergent. Okay. I think it's kind of curling here. Try to uncurl it a little. There we go. Okay. 21 I did. 11.6, 21, 23. Another one of those even factorials, I think. 23 summation 2 times 4 times 6 2n over n factorial. Okay, so absolute value of a sub n plus 1 over a sub n. 2, 4, 6, 2 parentheses, okay, 2 parentheses n plus 1, n plus 1 factorial, n factorial, 2, 4, 6, 2n. Now, this is 2n plus 2. So what's the factor just before it? 2n. Okay, so 2, 4, 6, 2n cancels 2, 4, 6, 2n. All of these cancel out except for n plus 1 in the bottom. So I have 2 times n plus 1. Remember, this is 1 times 2 times 3 up to n. 1 times 2 to 3 times n plus 1. So I have that, which is 2. That's greater than 1. Therefore, the series diverges by a ratio test. Okay. 11.8, 19. X minus 2 to the n over n to the n. It's perfect time for the root test because you can take the nth root very easily. So limit n approach infinity of absolute value of the nth root of, I can write it like this, right? X minus 2 over n to the nth power. That's the same thing, right? You can distribute the n. X minus 2 to the n over n to the n can be written like that. And then you just take off the nth root and the nth power. So it's a limit as n approaches infinity of absolute x minus 2 over n, which is 0 for all x. So r is infinity, I is negative infinity to infinity. Okay, 11.8, 29. 11.8, we did not have to do 29. So I'm skipping that one, whoever asked that one. Okay, 11.9, 13. Okay, that's going to take a while, and I know we did it before. Let me hold off on that for a moment. But whoever asked for 11.913, look back in your notes. It'll take a while for me to do it, though, unless I go really fast. 11.7, number 5, can I do it by a P series? 11.7, number 5, can I do a P series? The answer is no, because it doesn't look like a P series. Okay, P series would be 1 over n squared, but it's e to the n over n squared. Okay, that one I would do by the ratio test. Okay, so P series is only if you have 1 or a constant like 4. Okay, so ratio test, a sub n plus 1 over a sub n. So e to the n plus 1 over n plus 1 squared. Flip the original, n squared e to the n. The e stuff gives me e on top. And then I can write n over n plus 1 squared. And that approaches e as n approaches infinity. E is 2.718. It's bigger than 1. So the series diverges by the ratio test. In the long run, it looks like you just keep multiplying by e. Okay, 11.913, and I think I would have caught up. I know some of you just put something else in the chat, but I think I'm done with everything since the break from what I had there. 11.913. 13. Oh yeah, 11.913. That was the one that was going to take a while. So I'm not willing to do that unless that happens to be the last one, perhaps. So let's see what else there is. Okay. 11.10, 7, 19, 29, 35. 11.9, 17. And then I think I would have caught up again. Okay. So let me see how much of that I'm wanting to do. 11.9, I'm already on 11.9, so let's see. 17. Not sure if I did that one. I may have done it during office hours. X over 1 plus 4x squared. So let me start with 1 over 1 plus 4x, which is 1 over 1 minus a negative 4x. So first term is 1, common ratio is negative 4x. Since I'm differentiating, I need 5 terms, because after I differentiate, I'll have 4 left. 1 minus 4x plus 16x squared minus 64x cubed plus 256x to the 4th. Okay, so I differentiate both sides. 1 over 1 plus 4x prime is 1 plus 4x to the negative 1 prime, which is negative 1, 1 plus 4x to the negative 2 times 4, or negative 4 over 1 plus 4x squared. So that's the derivative of the left-hand side. 1 over 1 plus 4x, 1 plus 4x is negative 1, which is this. Okay, so derivative negative 4 plus 32x minus 192x squared plus 1024x cubed. Okay, divide by negative 4. So divide by negative 4, 1 over 1 plus 4x squared. So divide by negative 4, positive 1, minus 8x plus 48x squared minus 256x to the 4th plus dot, dot, dot. Divide that by negative 4, negative 4, negative 4. Okay. And then just multiply by x and you have what you want. So multiply by x over 1 plus 4x squared, multiply by x, that's easy, x minus 8x squared plus 48x cubed minus 256x to the 5th plus dot, dot, dot. Whoops, that's wrong. That should be a cubed, so that should be a 4th. Is that right? Yeah, that's better. Okay, 11.10, several questions there. Next slide. Okay, 11.10, number 7. Okay, first 4 terms, f of x equals cube root of x, a equals 8. F of x is x to the 1/3. F prime of x is 1/3 x to the negative 2/3, which is 1 over 3 x to the 2/3. F prime is negative 2/9 x to the negative 5/3, which is negative 2 over 9 x to the 5/3. F triple prime is 10 over 27 x to the negative 8/3, which is 10 over 27 x to the 8/3. Keep plugging in 8. Cube root of 8 is 2. Prime of 8, 8 to the 2/3 is 4, 1 over 3 times 4 is 112. 2 to the 5/3, 32. 1 over 16, negative 1 over 144, I think. 27 times 256. And I don't have time to figure this out. Okay, so I'll let you just figure that. I mean, the numbers are there, the rest is just arithmetic. So now for the polynomial, centered at 8. So f of x, x minus 8 to the 0 over 0 factorial, x minus 8 to the 1 over 1 factorial, x minus 8 squared over 2 factorial, x minus 8 cubed over 3 factorial, 2, 1/12, negative 1 over 44, and then this thing, 5, 128, 5 over 27 times 128, and that's as much as I'm willing to do for that. Oh, plus dot, dot, dot. Okay, you would actually have to work that out on the test, but I don't feel like doing that now. Save time. And 144 times 2, I can do that, 288. And maybe that's about it for that one. $19. Okay. Right, unfortunately, I did one which wasn't quite the same. F of x is x to the 5th plus 2x cubed plus x, centered at a equals 2. Okay. Now let's look at the directions. Find the t of the series. So I do have to go all the way out. So f prime of x is 5x to the 4th plus 6x squared plus 1. Second derivative is 20x cubed plus 12x. Triple prime is 60x squared plus 12. Fourth derivative is 120x. Fifth derivative is 120. And fn of x is 0 for n greater than or equal to 5. Okay, f of 2. Oh boy. 32 plus 2, 4, 8, 16 plus 2. I'm very susceptible to mistakes right now. I'm giving you the theory at least, since I'm going so fast. F prime of 2, 5 times 16 is 80, plus 60 times 6 times 4 is 24, plus 105, I think. At least you're getting the theory. So hopefully you get the theory, even though my arithmetic might be messed up. Plug in 2, 2, 4, 8, 160, plus 24, 184. Plug in 2 here, 60 times 4, 240, plus 12, 256. 4 of 2, 120 times 2 is 240. 5 of 2 is 120, and all the rest are zeros. Okay. So here we go. Centered at 2. X minus 2 to the 0 over 0 factorial. X minus 2 to the 1 over 1 factorial. X minus 2 squared over 2 factorial. X minus 2 cubed over 3 factorial. X minus 2 to the 4th over 4 factorial. X minus 2 to the 5th over 5 factorial. I can stop because all the others are 0. And let's see, 50, 105, 50, 105, 184, 256, 240, 120. So et cetera, clean up the arithmetic. I know this is 5 factorial is 120, so that's just x minus 2 to the 5th. And that's 10, I think. And maybe that's all I feel like doing. Okay, so anyway, that's the answer to that one, hopefully. Okay, yeah, there was a numbering issue, unfortunately. This was not supposed to be asked for. Okay, if I ask for 27 and 29, no, 29. Okay, skip 29. Okay, that was the skip part over here in the previous edition. Okay, so sorry about that. $35 arctan of x squared. Okay. So I start with arctan x. So you can look that up in the table. It's x over 1 minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. Arctan x squared, put x squared here, 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 and here. So parentheses over 1, parentheses cubed over 3, plus parentheses to the 5th over 5, minus parentheses to the 7th over 7. Just like any other function, what do I put in parentheses? X squared, x squared, x squared, x squared. So it's x squared minus 1/3 x to the 6th plus 1/5 x to the 10th minus 1/7 x to the 14th plus dot, dot, dot. And there we are. Okay, I think I've caught up that round. Let me check more. Okay, 11.9, number 11. Okay. Yeah, unfortunately, that one was supposed to be skipped also. Sorry about that. There's a lot of issues about using the previous edition. That was going to be too much work. So skip 11.9, number 11. Skip 11 also. Okay, I think I've caught up, but I could have made a mistake. This is where it's nice to have an assistant where the assistant can keep up with everything. So there are a lot of questions there. If I didn't get to your question, ask now, because otherwise I guess we're done for tonight. You can still ask questions at the beginning of Thursday, but I'm assuming most of you want to get it all out of your system, so to speak, today, so you would have as much time next time. So when we come in on Thursday, there's no new material. We're finished. We'll go straight to questions and answers, then break, then take the test. Okay. Anybody else want to ask stuff tonight? Otherwise, we're done for tonight. Okay. Again, I think I cleared out the chat, but I may have missed something. You know, I'm trying to look at the chat and do the problem at the same time. So I missed your question. Feel free to unmute yourself and just say it or put it back in the chat. Okay, I'll wait for a little bit longer. Let's see. If we see a better method, can we use that method on the test? It depends if it's a valid method. It has to be something that we've already done. So a lot of these problems can be done more than one way, for sure. But I think if you're talking about back on the integral test section, right? And you had one where you had to integrate something that was a little bit messy, right? 1 over n squared plus n cubed, something like that. To do the integral test is a little bit difficult, but if you want to say pick a different method like the limit comparison test, yes, that's exactly what I would do for this. I wouldn't want to integrate that for sure. Okay. Will there be the same number of questions? Yeah, I plan on still roughly 10 questions. So you'll just get a little bit longer to do the test, I guess. All right. Time is at 9 o'clock. So we still have time, but if you want. Okay. Any other questions, please? Otherwise, we're done for the night. If I missed your question in the chat, you might be saying, oh, he missed my question because there were so many questions there. I could very well easily miss it. So ask again or unmute yourself. If I missed your question, that's definitely a possibility. Okay. Anybody else, please? If I missed your question, ask it again. Wait a little longer. Okay, I don't hear anything. So we'll call it a night, folks. So you may ask questions at the beginning of Thursday. Otherwise, we'll break and go straight to the exam on Thursday. So quickly. So that's Thursday, the test. Tuesday, your homework is to ask questions from previous exams. And then the following Thursday is the final exam. Final exam day, that's all we're going to do. So no questions and answers for sure on the 17th. It all has to be on the 15th. Okay. All right, anybody else? All right, that'll do it for tonight, folks. All right, so good night. Go ahead and prepare for the test on Thursday, and we'll see everybody on Thursday. All right, good night, everybody. Have a good evening. Bye.
All right, thanks a lot, Professor.
Thank you.
Good night.
Good night.